Hello, 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 and welcome to tutorial number 43, I think, of our tutorial series, where we are going to look into two plugins this time around. And what we're going to aim for is first creating some sort of a structure analysis model with Kiwi 3D, because all of you have problems downloading Millipede these days. So I'm moving to another finite element analysis system. So that's going to be Kiwi 3D, available in Food for Rhino. And then once we have that analysis done, we will optimize it with I guess it's also a genetic algorithm, evolutionary algorithm, but it's not going to be Galapagos. It's going to be Octopus. And the reason why we choose Octopus because it has the possibility to optimize against 2, 3, or basically it's a multi-dimensional optimization tool, right? So it can optimize this the amount of beams versus the average length of all of those beams, right? So you have like two variables. With Galapagos, you can only do one or the other. It just basically takes one number and increases or decreases it. Octopus can take multiple numbers, right? So that's why it's multidimensional. Okay, let's get started. Here on my screen, you can see my notes. So basically, I just built up like a base test here, just if I get stuck, because it's a little bit tricky for me as well. So we need a form, right? To start off, we need a form. And what kind of form will we do? Let's do a cylinder. Oh, sorry. Before we begin, we need units. We need to specify what kind of units our file is going to be. So I'll type in units. And I'll choose meters. It's always a good idea to choose meters with these structural analysis tools, because usually they work with kilonewtons against a meter, right? Within that unit range, so to say. So centimeters or millimeters might yield weird results. Okay, so meters, that's done. So now back to creating a cylinder. So let me grab that, start it from 0, and I'm drawing it as a diameter. With a diameter, you can draw it with a radius as well, that's fine. So let's say, how much do? We do, as a radius, let's do 20. Yeah, 20. Yeah, sure, maybe. I don't know. Let's do 15, because I'm not sure about 20. And the height, what's a nice height? That is like 57, that's 70. Let's do 70. 70 seems to be an okay proportion. It's not great, but it's good enough. Let me go to shaded view. So that's our cylinder. I don't need the top and the bottom of it. So I will explode it and select the middle portion and hit delete to get rid of the top and the bottom. So it's basically just a single surface, right? Wrapped around from start to end. Okay, now let's make it a little bit more interesting. And for that, I could grab just, I could kind of rebuild it with more points and grab those points and kind of mess around with them. But I think I'll use a different tool, because it's nice to kind of, jazz it up from time to time. So I'll use cage edit tool. Cage edit, select control object, that's going to be a bounding box, world coordinates, 4 by 4 points is fine, enter. So we get this kind of a cage around our shape, and now if I grab these control points here at the top, I can kind of rotate them. Well, if I don't have snapping turned on, ortho off, I can rotate them. And I can mess around with the cylinder as I please, right? So let's see what we are going to do with this bad boy. Something like that, maybe. Maybe the bottom is also a little bit smaller. Something like that. And I want a pretty fat base here. and maybe it's a little bit higher up, and maybe it gets a little bit thinner here. Cool. So we have our cylinder. Escape out, select the cage, delete the cage, we don't need it, and I can rebuild it just to get rid of the convolution. 8 by 10 is probably going to be fine. Yeah, there we go. So we have a form, right? So then we will begin actually creating a system for that form, right? How do we do this? Where do we start from? Perhaps we need to start simple. Simple. We always need to start simple. Perhaps we need to start with a finite element analysis system, building that up, right? So that we have a framework. So let me hide the shape for now, and instead, let me create, let's say, a rectangle from 0, and I'll just type in 10 by 10. So 10 by 10 meters of like a rectangle, that's 10 by 10 meters, and maybe yeah, I think this is going to be fine. This is going to be good enough. So I'll just explode that rectangle so that all of the elements are separate. And I'll grab like, let's say this element and this element, these two elements. I'll copy them like so, right? So I basically have 1, 2, 3, 4, 5, 6 curves in total. Well, for those of you who want it to be symmetrical, sure, let's do it symmetrical. So 1, 2, 3, 4, 5, 6, 7, 7 curves. And let me reference those in and treat these curves as if they were beams, right? So let me zoom in. Set multiple curves. So this is a tutorial, right? Let me delete that. In Grasshopper, I double click on the screen and I type in CRV, which is going to produce an empty curve component, right? Container. And I right click on it, set multiple curves, and I select these curves here and hit enter. So now these curves are linked between Rhino and Grasshopper. I kind of assume that you have the basic knowledge of Grasshopper because this is definitely a more advanced tutorial. It's not a beginner tutorial. Right. So I want to simulate as if these curves are receiving load, like they have a weight to them, they are beams, and they are locked, let's say, on this point here and this point here, on these 2 points, right? So I just created 2 points there. I will reference in those points, point, right click, set multiple points, that and that, enter. And I'll just, so that I don't forget what these are, I'll just name them curves for beams. And these will be, so I scroll wheel, select the node, scroll wheel, click it, and choose to group it. I think the shortcut is G or something like that. I don't use that. Right click on the group, and then you can name it. So the points are going to be supports. Support points, right? Basically where the structure is locked in place. All right, so now this is where we start using, not Kangaroo, Kiwi 3D. Again, available in Food for Rhino. Very nice plugin, quite fast as well. So let's begin. For those of you who are familiar with the channel and with my videos, you know that everything that is simulation based, I do it from backwards, right? So usually you construct the definition from left to right in Grasshopper, but here I'm going to do it backwards, just like I would do with Kangaroo, or how I would do it with Millipede, because it it's easier to fulfill necessary inputs for the solver to work than it is to kind of build up the inputs and then connect them into a solver. I don't know if that makes sense, but it definitely makes sense for me, and that's how I do it. So let's start. In Kiwi, the solver is located under model, and it's called IGA, isogeometric analysis model, right? And by the way, the tutorial on Kiwi is going to be super redundant, like super simple. I'm not going to go deep into it. We just need values from this simulation, right? So it's going to be super simple. So we have a solver, and it doesn't work. It asks you to give parameter m. Okay, what's m? Analysis model. Okay, we need to construct an analysis model. So I go to model again, and I find a node that's called analysis model, right? Easy. Plug that in, and m goes into m. By the way, I will not be showing full names because it's going to get so convoluted. So bear with me. Bear with me. Draw full names off. So analysis model is here, solver is here. Connect those two. All right. What are other two? Path, location of file path. We don't want to export the file, so we don't need the location. And run. If it's set to true, it's going to run. And for now, it's set to false, and that's fine. We don't need it to be set to true, but just in case, I will have a toggle. Boolean toggle, I'll just connect it like so. Once I need to run it, I just make it true. Okay. This guy, to work, needs 3 inputs, right? A, E, and S. A is type of analysis. Okay. You can find it under analysis. These are 3 types of analysis that you can do. Form finding, linear analysis, nonlinear analysis. I won't go too deep into them, but for our application, we need linear analysis, right? So I'll use that and connect it like so. Okay. Linear analysis kind of works from the start, but let's just see what kind of inputs it needs. Name of analysis, we don't give a shit, and output setting. Okay, we do give a shit about what kind of outputs we're going to get from the analysis, right? And it says connect value list component to choose. Okay, so I just create value list component and connect it. Bam! It immediately gives us a bunch of tick marks. Super. Okay, so we have that working, and I'll come back to this in a bit, but let me just group it and place it somewhere here. And move this away a little bit. Displacement stresses and support forces. Okay, sure. I'll show what those do in a bit. So analysis model is done. Next is E, structural elements. Shell, beam, blah, blah, blah. We need beams, right? So I need to create structural elements. I can find them under elements. And here you have cables, beams, membranes, shell elements. So shell and membrane are 2 different things. Keep that in mind. But we need beam element here. Okay, that's a big boy. And notice how it's going to look like with full names. That's why I don't draw full names. Turn that off and connect elements to elements. Okay, now we ask it, what the hell do you need to work, right? We don't want to give it all of the inputs. That's going to take too long, but we need the bare minimum for this to work, right? So geometry of beam element, curves. Yeah. Curves for beams, super. Connect. That was easy. Second one, material. Right click, set data item. There's nothing that we can set, so that means we need to check here if there is something like with material. No. Oh, there we go. Material defaults and material. I'll just go for material here. Connect it. That's done. Let's see what kind of inputs it has for choosing a material. Name of material, optional, steel, Type of material, elastic isotropic. Young's modulus 200,000. I have no idea. Actually, let me Google that. Steel Young's modulus. I'm Googling it on another screen. Is this in KSI or? Hello? Young's modulus. It doesn't say, but it says 200,000. Anyway, I don't. Ten to the power of 6. So it's actually much larger, but we don't care. Then temperature coefficient, Poisson number. Why is Poisson number 0? Steel Poisson ratio. 0.265. 0.265 is going to be our Poisson ratio. This is, I don't know why I'm showing it in the tutorial, it's whatever. Strength of material, yeah, whatever. Close that. Actually, let me just delete it so that you don't get confused. Just plug in material and it's gonna work. Okay, next. Section of beam. Okay, is it a T-beam? Is it a square beam? Is it a circular beam? What kind of beam is it? If you go to elements here, you have box section, you have pipe section, you have section from profile. We will go for pipe section. I think it's the fastest one. Maybe the box section is faster, but I believe pipe section is the fastest one. So I will connect fastest one to calculate. So I drag and drop it here, and section, we just connect to the section input. What's A? Area of section. Yeah, we don't care. 2 inputs for the section component, pipe section component, is diameter and inner diameter. So basically, if you wanted to have a hollow beam, we don't want to have a hollow beam, we want to have all of these beams to be solid, and the diameter is 0.2 meters, which is 20 centimeters, and yeah, I can live with that. 20 centimeters for a beam. Depends, of course, on the structure, but like generally speaking, yeah, sure. Okay. Then we have curve refinement. Refinement for curve geometry. So that's it's basically how much resolution will you give the curve during the calculation. Right, so we just go to, that's not under loads, is it? It's under utilities. No, it's not under utilities. It's under results, supports, model, loads, elements. There we go. It's under elements, curve refinement. Okay, grab it, plug it in, and for now leave it as defaults. Defaults are kind of okay. Later on, I'll show you a few tricks here, and then you have a bunch of settings here that we will not be messing around. For instance, pre-stress, coupling features, and so on. And start, blah blah blah. It's going to be a pretty static simulation. Okay, so we have that done. Let me try and kind of make it as tidy as possible. Group that, and that's our elements. I believe this is the last thing that we need for this to work. Supports, what doesn't make the whole structure just fall down. No, sorry, 2 more things. One is loads, one is supports. So supports, what doesn't make the structure go down, just fall down. These 2 points right here are going to be our supports. Okay. So I will go to supports tab here, supports tab, and I'll choose support point, right? Support point, there we go. So now and I'll just immediately connect support output to support input. So here we have a bunch of inputs, and I believe, yeah, the first one is the actual point. So it's basically asking to give it actual points, and we have support points here, and I just connect them, and immediately the whole system starts kind of working, at least displaying, right? And my support points receive this these icons around them, right? Surrounding them. So those icons are from constraints, right? What kind of movement is the structure able to do on these points? So we have movement in X, Y, Z, and those are constrained by default, so that's fine. We keep it constrained, sure. We don't want the structure to move in either X, Y, or Z. Then you have constrained rotation and constrained torsion, right? We do want to constrain those two things. So I'll toggle, Boolean toggle, and I'll constrain rotation and torsion. True. Yes. So I set the constraint to true. Then we have coupling features, and we have direct supports. We don't care about those. But we do, in this case, I do want to constrain both torsion and rotation. Okay. And I believe the last one, before we can actually run the simulation, is going to be our external loads. Yes, it's going to be the fourth input. It does work without external loads, but I do want to add external loads here. So I will go for loads, and I will actually load the curves with some additional stress. So curve load, connect that, drag it down. So it connects to the loads input, right? Curve load, which asks us for curves. So let's say all of the curves that we have are, they have loads on them. Those are not curves, those are curves, like that. There we go. So it shows the loads. And then let's see, load type, dead load. Okay, dead load is fine. Load direction -1 and Z axis. You can see 0, 0, -1. That means it's straight down, and you can actually see it here. Yes, perfect. Load displacement curve for load. What the? I don't know. Again, coupling features and load case 1. I don't remember. Yeah, let's just go for load case 1. Oh yeah, you can measure different load cases in the same FEM model, FE model. So that's fine. All we care about is just connecting curves to this guy. Okay, we can run the simulation. So let me turn this to true. And saw how that, that black screen, we will see that black screen quite a bit. Let me actually do it again so that you can see. That DOS window. We will see that quite a bit. It's because Kiwi runs an external solver, which is basically a separate app. That's fine. Okay, so we have resolved model, right? Number of elements 7, number of, I don't know what GPs are, 160. What's GPs? Something about probably points at which the structure was evaluated, something like that. Okay, let's see the results, right? So to get the results, I go to the results tab, and I choose 1D element result view, because these are one-dimensional elements, right? So 1D element result view, I connect my mesh or my resulting model to my resulting model input here. And do I need a type? Probably. So I need a type. What kind of result am I showing? And it again asks me to give it a value list. So I will create value list right here. Connect it. God damn it. Connect it. There we go. And here I can see different types. And I don't remember which type I used. So yeah, that was just the regular one, just N. This type here. Okay, so the output that we get Why is it doing that again? So shear stresses are fine, but it's freaking out with N. What about von Mises stress? That's also okay. Okay, sorry, I'm getting ahead of myself. So N for some reason gives us like N is for newtons. I don't know. This is I'm not a structural engineer by any means, right? I just know that one Mises stress is usually something that I usually check and evaluate. I don't know why N is funky. Let's see if that also is the case if I have these beams rotated around this axis. Rotate 3D around the axis of the two supports, just like that. Oh, there we go. Now it's calculating. Okay, but you can see that the output is super big, super big. So we need to scale it down, right? And to scale it down, we use scale factor of 1. Right? Sorry, we apply a scale factor, and right now it's scale factor of 1. So I need to say 0.001, something like that, and connect it. That might have been a little bit too small of a number, 0.01. There we go. So now you can see what's actually, being visualized. I wonder why one Mises stress is so large. 0.00001. Zoom selected. Jesus Christ, it's still so huge. Shear stress. That's shear. And so, but we don't really care about, okay. Right now I'm getting ahead of myself again. We don't really care about the preview, those meshes. Those meshes do have indications about, the directionality and so on of the stress, but we really don't care about that kind of stuff. So I will specify N, because that seems to be the thing that works. And I will just look at the values. I don't care. Actually, let me disable the preview of this altogether. I don't care about, the graphics. I only care about the values. List of results. Panel. There we go. Or can we check deflection? No, we can't, huh? Let me check one thing. Sorry for making this harder than it is. Yeah, so we can check deflection for sure. And then we have our model, geometry, and deformed structural element. Okay. So we can kind of optimize against deflection as well, not against stresses. Do we want to do that though? And also, why the heck? Is it because of this load? Let me disconnect it. So now all the deflection is 0. Okay, so it's not because of this. Well, it is because of this, but I guess the value of load is 10. What if we give value of load 1? Is this like newtons, kilonewtons, meganewtons? What is it? I don't know. It is what it is, 0.0001. Yeah, anyway, let's leave it at something like 0.1. for the value. Let's come back and check out. Jesus Christ. Let's check out what we get here. So we get the deformed model. You can find it under results deformed model, and then I believe we can get 2D element result color plot, but do we really need that? Or maybe it's not even going to show us. No, it's not going to show us. Or T. What's T? Type. Connect that. Z displacement. Okay, that doesn't work. Okay, enough experimentation. Sorry for taking so long. Let's continue. We do have stresses here. We have values that we get from this particular load case, right? Super. So now I want to color the beams themselves according to what kind of values we get, right? And I can do that quite easily. But before I do that, let me hide everything. And let me make this into a cluster, right? So let's see, the inputs to this cluster are going to be value of the load. And actually, I don't need to calculate displacements, and I don't need to calculate support forces. Those two are unnecessary. I only care about stresses, so I untick those. Because that's what we're going to optimize against. Okay, so I need a toggle to be outside, and I need these. No, I don't need the scaling factors. Well, maybe I do. 0.001, something like that, like a smaller scaling factor, but I will have it dragged out here, like so. And then load type N, I will keep it inside of a cluster. Okay, so to make a cluster, what you do is you select all of the elements that you want to cluster into one group. You click the scroll wheel and you choose this icon right here, right at 12 o'clock. Click that, and it becomes a cluster. But you can see the cluster right now doesn't have an output, right? So I'll Control Z here, undo, and where it says values, I will say number. Those values are, their output is are a series of numbers, right? So that should help me now to cluster everything with a single output. Okay, now let's clean this up. Let's clean up this cluster. There we go, support points go here, and I can see that there are a few things that I want to kind of mitigate. First one is curves for beams has two inputs here. I don't want that to be the case, so I'll go into the cluster here. Why are you red? Doesn't matter. I'll go into the cluster, and where it says C, C is for curves, where I have the input C into my beams, and I have input C into my curve load, I will delete one of those, and I'll connect one cluster input to both of them, right? Save and click on the top left corner box, save and close, and now the cluster is good. So let me reset and see if that works. It actually doesn't. Oh, come on. Okay. I really hope that Kiwi 3D will work inside of a cluster, but it doesn't. So we will have a big ass definition here. I guess that's fine. Let me drag everything into correct positions. That goes here, that goes here, and that goes here. All right, let me just call this Kiwi 3D. Okay, So now we have values, right? And we have our beams, and I need to colorize these beams, like these curves, according to these values, right? So the curves that have a lot of stress need to have color red. Curves that don't have a lot of stress need to have color green, right? How do we do that? Well, first of all, the curves need to have need to be three-dimensional, right? They need to be a mesh. So I will use, I believe it's in Pufferfish. So in Pufferfish plugin, I will use a tool that's called pipe, parameter pipe mesh. This guy right here. And I'll pipe these curves, just like that. Easy. Then I will give it a radius of the same radius as I have here under here I have diameter of 0.2 for the beams, so here the radius needs to be 0.1, like that. These are very thin beams for this kind of a structure, now when I think about it. Anyway, then we have parameters, U and V. So for parameters U, I will say range. This is basically how many subdivisions do we have along the beam. So for parameter U, I will use a range component, and for the steps, I will use 2, number 2. So it basically only has start, middle, and end, right, as subdivisions. I can actually show you this with preview mesh edges. This is the middle subdivision. If I increase the steps to like 5, then I have more of these, right, along the line. But I don't need that many of them, so I'll just use 2. And then for the parameters, the V parameters, here it's using 5. That means a cross section of this is kind of like a pentagon. No, it's not a pentagon. It's for some reason a rectangle. Oh, let's keep it as a rectangle. We don't care. Oh yeah, because of the start and the end. So it is a rectangle. So let's keep it as a rectangle. We don't want to have too many polygons in our final structure. Okay, so these become separate meshes, right? And I need to colorize them, right? So I will be using deconstruct mesh component, deconstruct mesh, because it gives me vertex, face, and color information. And I will be using construct mesh component, vertex, face, and then now I can add color information to these meshes, which is very important. And the color information is going to be like added from this number, from these values right here of the stresses, right? So I have 7 beams in total, and notice how here the data tree, not the parameter data tree, there we go. How here the data tree has 7 branches. Every branch of these values belongs to one beam, right? And it's not messed up, meaning that all of the pipes here will correspond to the value to the data tree here. Great. So now for the values, I need to do some math, right? If I just check them out, I can see that some values are positive, some values are negative, some values are just straight up 0. So 0 is for this beam right here, which has both of its ends locked. So of course it's 0. And so on, right? So we have a bunch of values, and why are these the same? It's strange that they are the same. No, they're not. Sure, let's use n stress. Okay. So with these values, what do I want to get from them, right? I want to get an average stress within the beam, right? So this is all of the stresses within the beam at different cross sections. I want to get an average stress, and I want to get, what else? I want to get the maximum stress as well within the beam to see if there is a point where the stress is really high. So how do I do that? Well, let's get average of all of these like values. So now we have averages, but some of them again are positive, some of them are negative. I don't like that. I want it all to be positive, so I will say what's the name of the component? Absolute component, like that. So now all of them are positive. Okay, so here I get a number, like series of numbers rather, that are average stresses, right? Okay, and now I need the maximum stress, right? So within these values, back here, within these values, I need to find in each data tree, in each list, I need to find the highest number. So I will sort the list, so it goes into K, and I will reverse the output, right? Because it sorts from smallest to highest, but I need from highest to smallest, so I will reverse. Right-click on the K and reverse the output, like so. So now it's always going to have the highest number here. Oh, but in case of negative values here, it's going to mess up. Okay, so what we need to do is the absolute needs to go right before the average and the sorting, right? So now all of the we get average of all of the positive values, and we get the sorted all positive values that are sorted. I'm just thinking what happens with a beam that has negative values on one side and positive on the other. That becomes bad. But if we give it positive, then it becomes fine. Yes, okay, good. That's actually, yeah, that's how we need to do it. All right, so here we have highest values always at the top, and all I need to do is just do list item. List item, grab the first item of the list, bam. We have largest values, right, or largest stresses within each beam. Okay, so we have an average, we have the largest one. How do I visually show that what I care about is, I do care about the average stress within a beam, but I also really care about what's the maximum stress within any cross-section of the beam, right? I can influence the number, the final number, with the largest value here in the stress. Let me just do this. Largest stress per beam. Not per beam, but per multiple cross sections of a beam. And here, and here it's going to be average stress per all cross sections of the beam. right? So average versus largest. So average is not enough. We need largest to have a lot of input over, you know, our evaluation of the structure. So what I'm going to do is I will give these two values weights, and weights are importance, right? So I will multiply the average one, or rather let me multiply the biggest one. No, the average one, sorry. I will multiply it by a value between 0.1 to so dot 0 point, or rather dot 1, right? So I can multiply it by this range of values. So, right, and then we get smaller numbers here, right? So it has less influence if we do this. Multiply. Come on. Multiply. Oh my god. Multiply. Multiplication. There we go. We'll multiply the weighted. Let's call this weighted value. We multiply it with the base value of the largest stress. Okay, thus we get really large numbers here. That's expected, that's fine. I can clamp those numbers by just, or not even clamp, I can just divide. Hello, division, I guess then. There we go. Division, so I can divide these numbers by 1,000,000. So 10 power of power to 6. So I divide them by 1,000,000 and then I get reasonable values. Maybe 10 to the power of 6 is too much. 10 to the power of 5. Okay, that's fine. Whew, we're getting there. Okay, so these values here, they are not like stresses or anything like that, but they are my evaluation of how fucked a beam is. If the value is real high, then the beam is real fucked. If the value is really low, then the beam is fine. The beam is okay, right? And I believe, let's just double check, beam 2 should be this guy right here. Let's just double check if, because it's being held by 2 points, so it should have least amount of stress in it. Let me enable this, and please be beam 2. Why are you not showing? Are you here? It's actually beam 3. Oh my god, oh no. And how does beam 3 look like? Beam 3 is one of the most fucked ones. What if we look at the different stress? Yeah, so beam 2 is actually with N stress, beam 2 is fine, but for some reason the N stress gives us the incorrect answer. Okay, what about the all trusted 1 meso stress? Okay, let's just use 1 meso stress. I always use that and it seems like then 1 meso stress. Oh no, wait, 1 meso stress is also bad. Not bad, but doesn't behave the way I want it to behave. So this is where you can actually see how I don't know. I don't know these things, right? We want to optimize against something, and here I'm just scrambling and trying to figure out which of these works. So it seems like utilization works. What's M1? Let's not use that. So M1 seems to be working as well. Let me just grab this and put it here. So everywhere where we have 2, and I believe 6, where is 6? 6 is here. Why is 6 doing that? Can we visualize? No, we can't. Okay, so cross section looks like that. And why are all of the values the same? Because all of the values are 1. Okay, sure. N looks like that. And N is actually correct, right? Or am I... Yeah, N needs to be... Yeah, N is correct. So that means my math is wrong. That means I messed up with my math. So let's test it out. So if we do absolute values here, then everything gets positive. Beam 3. It's that. Then we get average values. Okay. And then the output 2. Why is it 2? Wait. Oh my god, please don't tell me this guy starts counting from 1 and not from 0. I swear to god, if it's counting from 1 and not from 0, I will lose my shit. Okay. That's 2, that's 1, that's 3, 7, 5, 6, 4. God fucking damn it. Okay, so it's counting from 0, not from 1. Sorry, it's counting from 1, not from 0, and this is why there is a disconnect between what I'm getting and what in the data tree and what it's showing here. And Jesus Christ, don't do this to me, TV 3D creators, don't do this to me. Anyway, this is correct. This is fine. N is fine. We can actually go for von Mises stress. And all we need to do is just divide the values by like 10 to the power of 6, and then we will get some reasonable numbers here. Okay. So I was... Anyway. Remember that mesh that we want to color? Now it's time that we color it because we have values. We have 6 values that we will use, right? Or 7 values that we will use. So to do that, I will use a color gradient, and I will say that the lowest limit is 0, so no stress. And largest limit, I need to actually see the largest limit. And I can get it from here, from these 7 values, I can get the largest limit. But the problem is that they are right now in separate data branches, data tree branches. So I'll right click on it and choose to flatten. Right, so now they are in one list. And I can say, what can I say? I can say, yeah, sure. Let's do sort, just like we did with the previous one. Sort, and then let's do list item. There we go. Oh, and reverse the sort so that we get reverse the output of the sort so that we get the largest number. And that's going to be the end, like the largest value on this side. So 0 is going to be here, largest value is going to be here. Let's right click on the gradient, go to presets and choose a nicer color range from green to red. Okay, and now for parameter along gradient range, for that parameter, I will be using the results, right? Because those are the results within the beams that I want to visualize, right? So I do that. That's a little bit convoluted. Let me create a number component, connect the results here, and then connect the number component to the respected inputs so that it's a little bit more. Yeah, that's a little bit more clean. All right, so now we have a gradient, and I could technically just take it and connect it, but notice how this is grafted and this is not. So this is just a single list, while the output here is like these two outputs are in separate data branches. I want to graft tree. I want to graft this output here and connect it then like so. Yay! It works! And we can actually see the two beams that are being screwed over. The problem is that everything else seems to be green. So let me move the yellow slider a little bit closer to the green side so that we get a full-on display. Yes. Okay, so that works. We get a bunch of meshes, and then I can just make them into one. So mesh join. Nope. Mesh join. Oh yeah, and we need to flatten the input of mesh join so that it actually has all of them in one list and it can join them, and the output is going to be a mesh. Okay, this part right here, I will create a cluster of it, right? Because I don't really need it to be, to take up that much space. So piping, deconstructing, getting the colors, reconstructing, getting the mesh, getting a single mesh. Let's create a cluster. So I'll select all of it, maybe except the radius, because radius is important to be able to change easily. So I'll select everything else except the output, mesh, and the radius. Scroll wheel click, cluster, bada bing, bada boom. Okay, let's call this beam curves. Right click, call this radius of beam curves. Right click on this one, call it values from FEM, finite element model. And the output is mesh. This guy. Yay! Okay, so we have that going on, which is great. And actually that single wire is super long, so I'll right click on the beam curves input and wire display. I'll just make it hidden so that it's not too much in our face. Whew, we're getting there. We are getting there. Now, second part, we need to apply the same FEM analysis to our building, right? Or whatever this is. Maybe it's not a building, I don't know. To this thing, right? So I will just select all of the stuff that I did, and I'll just delete it. Because all we need to drive it is the support points and the curves for beams, right? So how do we do this? And there are many, many ways of how we can do this. Let's say I want to optimize the envelope for the envelope. I will create a bunch of points on this envelope, right? So first thing is I need to reference it in as a vrep or as a surface, or as a surface, srf. Right click, set one surface, super. Then I need to, how do we do beams here on the surface? We could do like a grid, and then we could distort the surface, but that's kind of boring. Or maybe it's not. Let's think. Oh, we can use proximity 3D, sure. So I'll teach you how proximity 3D works. It's under mesh, triangulation, proximity 3D, not proximity 2D, proximity 3D. Proximity 3D asks us for a bunch of points, and it will connect them with lines, and those lines will become our beams. So we have a surface, we need a bunch of points on the surface. I could do it randomly with populate geometry, right, and just populate it with points like so, but I don't want to do that. Instead, I will do evaluate surface, and this is going to be the surface that I evaluate. And make sure that you right-click on the evaluate surface input, S input, and choose to reparameterize. Okay, so now I have the possibility to evaluate this surface at any given point with two numbers, u and v coordinates. Okay, that's good, but can we do better? Well, first of all, this will, by the way, this will only work with a single clean surface, right? So keep that in mind. Like pipes, spheres, and so on will work, cylinders will work, a box will not. Or just a, a nice surface will also work. Okay, so UV evaluation. I will create a logic where we use points where we use numbers to points. Numbers to points component, and connect it to UV input here, and you can already see a point has been, why are you here? Wait, you're not that point. Hide. Okay. It should be somewhere here. Is it not creating it? It is creating it. Why is it there? Hello? Oh, because the numbers are shit. Okay, don't worry about it. So numbers will be converted into points, which will be used as UV coordinates. That is fine. And the way this works, by the way, is if I grab a panel, it just gives us 1, 2, 3, because here the default input is 1, 2, 3, and here we have a mask of X, Y, Z. So first of all, I need only two numbers. So I'll right-click on the mask input, and I'll choose set mask, and I'll choose X, Y. Right? Now it's freaking out because it has three numbers and I have a mask of X, Y. But I can kind of fix that with just giving it two numbers. So let me just create a panel and real quickly show you. 1, 2, 3, 6, 6, 6, right? Two numbers. Right-click multi-line data and connect it like so. So now it's 1, 2, 3, 66, and 0. So I need to do, and it can be used as UV coordinates as well. That's why I'm doing it. So I can do it here in the same manner, right? I right-click on the mask input, set mask XY. And then I have numbers as list, which I can create a bunch of numbers, and I can create them with sliders, but I don't want to have a million sliders. So instead I will do gene pool. Gene pool. It's basically the same thing as a million sliders, right? And I'll connect that gene pool to the N input here, but I need to edit it, right? So right now, since we used reparameterize here, I need to change the values to be from 0 to 1, right? Instead of from 0 to 100, because that doesn't work. So I will go to edit here, right click on the gene pool, click edit, and for minimum I'll keep it as 0, but for maximum I make it 1, right? And then for gene count, I need a number that divides by 2, right? And basically, for every, let's say, let me show you an example. So gene count 2, right? Hit OK. I have two numbers. Those two numbers get converted into coordinates. Basically, it becomes a single coordinate, and it gives us a single point on the surface. And if I move these two values here, one moves along the U direction or V direction, the other one moves along the U direction, right? Easy. If I right click, edit, and I give it gene count of 4, okay. Now I have two, like a set of two coordinates, because here points from numbers gives me 2 points, and it translates into two coordinates, and now I can move them individually, right? So any value, any gene count value that we give it here is going to be divided by 2. So I want, how many points do I want? Let's say I want 100 points. So I'll give it gene count of 200. And right click on the gene pool and just choose randomize 100%. So now I have 100 points floating about here in this example. Okay, those 100 points, let me just create point component here so that we don't need to see the planes. I'll hide the planes, hide the surface, or maybe I don't hide the surface. So those 100 points are right now randomized, right? And I can basically have the ability to move any one of them to anywhere I want. And this is very important for later optimization of the structure. Okay, so we have a bunch of points here. I connect points to point input of my proximity 3D, and already it interconnects them into this kind of a structure, right? Great. You know, kind of works. I think that's fine. If you want to have more possible connections, then you can increase the group number of closest points to find, but I don't think that more than 5 is viable. Maybe 6. Let's try set integer 6. So just basically for every point finds the closest 6 points and makes connections to them. Okay, that's one thing, but the problem now is, wait, what's the problem now? Oh yeah, if every point is finding its closest neighbor and drawing a line to it, that means that closest neighbor is going to find the same point and draw its own line to it, right? Basically, we have a lot of duplicate lines here. So we need to get rid of those. First of all, I will right-click on the links output, L output, and choose to flatten. And then I will use Kangaroo's tool that's called remove duplicate lines. I have, for some reason, 2 of those, but remove duplicate lines. So now there are no duplicates anymore, which is great. And now we can use these as beams. And it's doing the calculations, blah, blah, blah. I'll just close it because I also need support points. Actually, let me stop the simulation. So I need support points because right now this whole thing is just going to fall down, right? Not great. How do we get support points? Well, how do we get support points? Well, we do have a lot of points here, right? Actually, all of the necessary points. I can just ask if those points are close enough to the ground to be considered supports. So I can take those points and I can deconstruct them into XYZ coordinates, and then I can say, is Z smaller than how many meters? Let's say there are columns like, let's say 1 floor, so let's say 5 meters. Is he smaller than 5 meters? Like that. Cool. And then we get our answers, yes or no. And with those answers, we can cull pattern. We can cull this whole list of points to just have those that are lower than 5 meters, like 5 meters or lower from the ground, and connect them to a support points input. Okay. Now let me disable preview of everything. And here we have it done. We have that part of the definition done. Radius is fine. Actually, I want the radius to be a little bit like this is very thin. Let me increase the radius a bit here and also increase the radius or the diameter here. So where's the diameter? Right here. Diameter, I will say 0.4. There we go. And now we can run the simulation, right? So now it's going to take a little bit longer. But it gives us the result. Cool. Apparently there's a lot of stress in this beam here. I don't know. I don't know if my skills with this is correct. My knowledge of this is correct, but maybe. What if we give it n? Does it recalculate? M1? Cross-section. Oh, cross-section is going to be constant. Utilization. N stress. Shear stress. There's a lot of shear there, huh? Shear stress 2. MT. No idea what, for instance, MT means. Either way, let's go for 1 mesos stress. Okay, so we have a big portion done. There's still one last thing to do, and it's actually optimizing this bad boy, right? So right now I could kind of move these guys around and try to... Actually, I need to save this, I think. So I can move these things around and try to optimize, but just a second. That will take forever, so I need some sort of a algorithm to do that, and I choose to use Octopus. This tool right here, multi-objective search and optimization. I just click it and drag it here to my screen. And it's Octopus looks weird. It kind of looks like Galapagos, I guess, but it does look weird. It has a phenotype input. Phenotype is basically a mesh with what kind of output, what kind of mesh do you get with given inputs, right? So in our case, the phenotype is the mesh here, the mesh output here, like that. That's the phenotype. Okay, then we have genome. So this is what kind of parameters is this optimization tool able to change. So genome is stuff that changes, and genome in our case is our gene pool right here, because it should be able to move all of the points around. Like that. Okay. Now, and notice how I drag it backwards from the Octopus to the gene pool, and well, not here, but for these two inputs, you need to drag backwards for them to work. Okay, so we have that, and now we have multi-objective search and optimization. So this is the objectives that it's going to search for. Okay. The way this works is we can give it, let's say, two. Let's go easy. Let's go with two objects or two things that it needs to search for, right? Let's say what would be the best. Let's say it needs to minimize the stress. If we just say right now with this model that we have, if we say minimize stress, what it's going to do, it's going to move all of the points into the same position, and it's going to make a bunch of small beams, right? And all of those small beams are going to be, all of those small beams will be really strong, but it's not going to make sense. So optimize stress, but increase the mass length of beams, right? So measure the length of all of the beams and try to increase that. So first of all, reduce stress, right? Here I have my values, right? But the thing is that Octopus will always try to increase stuff. So how do I make it reduce? How do I make Octopus reduce? Well, if I do negative, right? Then suddenly the values that were wrong, let's say, okay, let me give you an example. I guess I'm getting tired. Let me give you an example with Scribble maybe. Let's say the score that my structure gets, let's say this structure gets a score of 50, right? And it's let's say this is a bad score, right? So another structure, basically the larger the stress, the bigger this number, the bigger the score is, the worse the structure, right? So more shitty structures get worse, get higher numbers. It's basically a score of how shitty a structure is, right? So I have another one that's 500, much more shittier than this one. Okay, so I have these two values, and those two values are going to be simply, from all of these values, I just do mass addition, and that's the score, right? So this structure is, the shittiness score of the structure is 30.19, right? So let's say, we have one structure with 50, one structure with 500. And right now the problem is that our optimization tool will try to increase the score, right? So it's going to try and produce as shitty of a structure as it possibly can. What we want it to do is we want to decrease it. So if I say, give me negatives of these, right? Minus 50, minus 500, then the algorithm, the Octopus, will try to increase the number, and thus it will try to move away from 500 and closer to 50, right? So I reverse the logic. Okay, so all I need to do is just add negative to my result, and this is my score, right? So let me create a number token here. That is score. And let me group this and call it score. And I can, just to be clear, I can call this wellness, if that's a word, wellness score, and this is shittiness score, right? So shittiness score, a negative of it is the wellness score. Okay, we have that. Then I need to measure the length of all of these beams, right? So if I go right back here, curves for beams, CRV, I will just connect it like so. Right click on the input here and choose to go to wire display hidden. And just drag it, just drag it next to my goals here. So I have all of my curves. I can use length. I can use length to measure the length of all of them. And I can use, so I measure the length. What else do I do? I use mass addition. So I add all of the lengths of all of these beams up into one number. And that number here is 3000, right? So this is number, and I'll call this, is it the word cumulative? Cumulative length of all the beams. So I have that. I also want to somehow incorporate the fact that the structure, all of the points need to kind of reach the top, right? So I will do a bounding box of, how do we measure the height of things? So I will take the surface and I'll, like the starting surface, and I'll create a bounding box of it. And I will, maybe I do it here in the high up. So I create a bounding box of it, and I will evaluate that box at two different instances. And I know this is the lazy way of doing it, sue me. I will evaluate it at instance 0, 0, 0. And also at instance 0, 0, and then for here I will use 1. So basically these 2 points here, the bottom point and the top point. And I will just measure distance between those 2 points, and thus I know how tall the structure is. Okay, so I have that number. And I'll call it structure height. And this is kind of an annoying, like it's not pretty, so I'll just make a cluster out of it, just to make it okay. Let me wire display hidden so that there are no ugly wires here, and just drag all of it to the right where we're working. Okay, so here I have structure height. I need to kind of do the same thing for all of the beams, right? So I'll borrow the cluster actually. This is turning out nice. I'll borrow the cluster, and here I can actually show the wires. Borrow the cluster, and I get, why do I get a bunch of them? Oh yeah, the bounding box needs to be not per object but union box. So I double click on the cluster, go in here, right click, union box. Click on the top left corner of the screen, save and close, bam, cluster works. And now the output is going to be a single value. So it's actually not structure height, sorry. This is envelope height. And this, the new one, is going to be structure height. Okay, so how do we tell that the structure is too low. Well, we just subtract from envelope height, we subtract the structure height, and we get a number, right? 0.5 or whatever. Wait, do I need to do that? No, I don't need to do that, sorry. So we don't need the envelope height at all. All we care about is structure height and making it as high as possible, right? That's it. Yeah, so, okay. Well prepared for the tutorial. Well prepared. Anyway, we have structure height and we have cumulative length of all of the beams. I need these guys to be weighted and then added up. So how do we do that? Or not, maybe not even added up. I can apply weight to this structure height, let's say weight of 2. And I can get this value and use this value to multiply this. So structure height becomes twice as important as cumulative length, and I think that is correct. So let me multiply again. Cumulative length and structure height. So here I get a value, an output value, which I'm going to, it's a number, right? So number component. I'm going to group it and I'm going to call it form score. So now let's think. It's going to try and increase it, right? It's going to try and increase this value. So thus, it will try to increase the structure height and try to increase the cumulative length. The higher the structure, the worse the wellness score is going to be. Okay, great. So that's exactly what we want. We want two inputs that are messing around with each other. What's the name of it? Let's just call it two inputs that are messing around with each other because I forgot the name, the actual terminology of it. Anyway, we have that done. And we will merge. So these are two numbers. We will merge them into one list and also create a number component here. Why is this grafted? Hello, don't be grafted. Let me just flatten input here, flatten input here. There we go. And call this both inputs for Octopus goals. Right? So I have my Octopus here, and I just connect it to both inputs for Octopus goals. Okay, now I need to give them names because these here are just numbers. They don't have names, right? I need to give them names. So how do I do that? Well, that's actually really simple. I just create another merge, like so. And I create two panels. Panel 1, copy paste, panel 2. That and that. So my panel 1 is going to be the wellness score. So I just call it wellness score. Right? And my panel 2 is going to be form score. Right? And basically now I just create a text component, empty text container. I call it names of things I optimize. I don't know, something like that. And holding down the shift key, I will connect from O output. Hold down the shift key, that's important. Connect from O output to the new names of things I optimize input here. There we go. Octopus is ready to go. Yay. Actually, let's look at this. So now we've done the, actually I don't need this anymore, I can delete that. Now we've done the whole shebang, and I accidentally moved the slider. Yeah, calculate. Done? Oh, come on, stop, cancel. Okay. So, shall we? Let me save everything first, just in case it crashes. And let me run no, not this, run Octopus, right? So, double click, opens up this window. Yeah, I know, it's a big boy, but we will figure it out. So here you'll have all of the all of the variations, right? When you have a single objective optimization, it's a linear thing, right? So you don't need this kind of graph. But when you have multidimensional optimization, on one side you will have the wellness score, while on the other one you will have the form score, right? So those are axis 1 and axis 2. Then I will just choose to diversify parameters, and that's going to be axis 3 upwards. Don't worry about that part. I will just do it. Just click there. Okay. Then we have the scale of meshes. Right now there are no meshes here, so we can't mess around. So this is visual, and this is settings for optimization. If you're a first-time user, I suggest using defaults, right? And yeah, let's click start, and I'll just give it a few minutes to do its thing. Actually, I will hide my webcam to save on battery, and then I will click start to give it a few minutes. Of course, I will speed this up in the video, but yeah, let's just give it a go. Start. All right, and as it's doing it, I believe I can still, no, I can't move it around. But you can see here, why did it minimize Rhino? Let me stop it for a bit. Oh yeah, I know why it minimized Rhino. So you can always pause and stop, right? Minimize Rhino and start. That's why. So I'll untick that because I don't want Rhino to be minimized. And actually, while we're here, let's look at what we have so far. So here we have the first contenders, so to say, right? And can I zoom into them? I can't really that easily zoom into them. Oh, I can. If I do it slowly, I can. So we have a few contenders here, showing, you know, the different meshes, and I can color according to, let's say, wellness score, right? So the better the, wait, it needs to be here. So the better the wellness score, the further it's going to be away from the 0, 0, 0 coordinates. So it's something like this. It's actually fine. Okay, let me let this run for a bit, and then we'll come back to it and investigate what kind of output we got. So start. Okay, we are back. So this is what I got after, I don't know, 5 minutes, maybe, something like that of running this. And you can see some of the values are here in the top. That's due to genetic diversity. I can remove that, and all of them will be placed on my grid. Just so that it's not too convoluted. So now with this with these tests, I can see that a lot of them are being placed at 0, and I believe they are being placed at 0 in parts where probably where it doesn't catch any points at the bottom of the structure. So that was my mistake. That was a mistake that I did, not introducing an additional check whether or not there are supports that are being calculated, right? Because sometimes all of the points are going to be higher than 5 meters, right, above the structure. But if we look at it, look at the structures here, somewhere here, we can see that those are right between the form score and the wellness score. So why is the wellness score here 0? There's many wellness scores that are 0 here. I would need to kind of revisit this and investigate it again. I assume there are at least a few engineers that are right now screaming at the screen and telling me how wrong I am for using some sort of the way I constructed these values for testing. I would encourage to yell at me in the comments and to kind of explain how the wellness score of the structure should be done and should be constructed, so that I can revisit this and learn. Because again, I'm no engineer, so I don't know these things. I'm an architect. I just know the basic principles of things, but definitely don't know too much about the subject. But I do know how to make a model that works. Okay, so with that out of the way, let's just choose one that we think is kind of okay. Maybe this guy here. All right, let me mark it. This one here. And let me, or maybe I should just round them off. So I can easily, I just click on the mesh, right, on any one of these meshes, and I can mark them, or I can unmark them to basically select the ones that I need. And I can right-click, I can click on it, right-click on it. Hello? Why can't I right-click anymore? That's weird. Did I click too many times? Probably have. Ah, there we go. So you don't right click, you just left click on it, and you can reinstate solution so that that solution is being passed here. Oh, and look how pretty this is. So these are all of the solutions being showed at the same time, and it's actually located here, 53 phenotypes of these meshes, and I can actually showcase them. I can showcase them by moving them. Why is this crashing? Oh no. Okay, it's not crashing. It seems to be crashing. So I can move these 53 meshes onto some sort of a grid, right? So I will just create a grid. That's not how you create a grid. You go to vector, grid, square, onto a square grid, and I will say that the size of the grid is every 50 meters. Why is this? Hello? Why are you lagging? Is it because of... Yeah, I think Octopus is being a little bit wonky. Anyway, let's do that. And what if I close this? I'm scared to close it because then I would need to run this again, but let me just close it and see. Okay, if I close it, it's still here. That's great. So I have my grid and I have my my size of the grid cells, and I have extent in X and Y. So let me just have enough of them. So here I know that I have 53. So if I do like 10 by 10, that's going to be 100 grid cells. So let me do that. Oh, it's actually going to now lag every time when I do this. Well, okay, bear with me. It's going to be a little bit slower. Okay, so we have that. And then we have 121 points. Let me flatten those out. We only need 53 of those 121 points. So I will just say split list, split this list at index 53, right? List length. So I measure the list length of this. And I plug it into I, right? So the list gets split into 53 and whatever 121 minus 53 is. So the first one is 53, that's what I want. And I basically just want to move all of these instances from 0.000 to one of these points. So I will do construct point. I'm basically just creating a vector for movement. Construct point, that's by default 0, 0, 0, right here. And then I create vector between 2 points. From here. Oh, this is making me slow down, I guess. I guess that's fine for pedagogical purposes, that I do it more slowly. So from the starting point to the one of these points, right? Or 53 of these points. I have 53 vectors, I have 53 meshes, and I move them. So I'll just connect vectors to the translation input here. Once I have that done, I can enable preview of this, and I can see all of the different variations here. So the red ones are crap. I can immediately disregard those, but the green ones are not crap, right? So let me bake those out. Fold, okay. Is it baked out? Yes, it is. Okay, great. So I have baked those out now, and I have my all of my structures here visible. All right, so we have that done. And the principle of it, I hope it's clear. This is red. Input string was not in the correct format. I don't know what that means. Does it mean that number of GPs is 0, number of elements 358? Okay, what if we... Sorry, now I'm just interested. What if we disconnect this part, this whole part here? Is it going to crash? No, it's not. And what if I run this again? So it's still creating an error. And I wonder why is that? So this is the error that we get, or is it not? Let's see the model. The model looks like that. So this is the incorrect output. Oh man, cell mesh hide for a bit. So for some reason this gets broken. Could it be that it gets broken because there's at least one point that is too close to, like it's too small of a beam, so it's freaking out. Let me try to remove duplicate points here. $99. Yes, I believe that is the case. So some of these sliders gave us 2 points that were the same, and now it's actually calculating. I think I fixed it. I think I fixed it. Yay. Because now this is correct, this is happy. 94 seconds though. That's a little bit long, and now we connect this to everything else, and it should give us a viable result. So sorry, I forgot this test for if there are any points that are duplicate. But either way, with this done, it now should optimize properly. I will not be doing that here because this is just a concept, you know, that how to work with this, a tutorial about the concept on how to work with this. If there are any engineers watching, give me suggestions on how to improve this wellness score, because it seems like it's moving too close to 0, or maybe it's 0 because it makes mistakes. Should we run? Let's try it. Why not? So I will save the Grasshopper file and I will try it again. Double click, reset the whole simulation, color along the wellness score. So C is for color. Let's hit that start button and see. And this is probably going to be a little bit slower. So we have one that has wellness score of -1. How can it have minus score? Oh yeah, -1 is fine because our wellness is in the minus. Then it has -121. Let's just grab like 5 of them, right? And once we're done, we're going to finish up here. So while this is doing, let me do some shameless plugs for the YouTube channel. First of all, these files that I'm working on, of course, you can follow along the tutorial and you can build them up yourselves. I think this is a very good way of how to learn. But if you're a lazy bastard, then you can check out the Patreon page, which is in the video description. And if you become a member in the Patreon page, then you get these files for free, right? If you're in the Rhino supporter bracket, let's say it like that. So check out the Patreon page if you want to get this file for free. I also have all of the files from all of the previous tutorials there as well for you to download if you start supporting the channel. Then So that's one thing. Another thing is if you become a member, become a member on YouTube. So subscribing and becoming a member are two different things. And I can actually show you here. If I go to stuff, YouTube, resources, badges, right? So if you become a member, let me make these bigger. There we go. At the first month of being a member, just as you become a member, you will receive this badge right next to your name. So in every chat that you participate in, this icon is going to be displayed next to your name, and you will be the small grasshopper, right? Then after, I believe it's 2 months, after 2 months of being a member in the channel, you become a high resolution grasshopper, right? So you're fancier. Then after, I believe it's 6 months, you start looking like me, right? Grasshopper, guru guy, I don't know. And then if you stay a member for at least a year, then you're like me, only that you can shoot lasers from your eyes. So you're like a better version of me at that point. And you get my deepest gratitude. So that's that. And also you get a bonus thing. It's an emote that you can use in any chat on YouTube, during live streams, which is basically my face every time when something goes wrong. Right, so you can mess around with that as well. Just some small fun things for the community, I think. Okay, let's stop the simulation, or optimization, rather. Let me wait for this to finish. And now let's investigate. This should be much better. So, zoom in, scroll, zoom in. So these are the structures, and some of them seem to be quite decent in the wellness score, like -1. So I believe there is still some sort of underlying issue there, but also now they are more diverse in the form score, right? So the smaller the form score, the more issues the structures have in terms of distribution of beams and so on. And it's like you can see this whole opening here that's not good enough, right? So that's the form score. The higher the value is, the better the distribution is. So here you have a bunch of like meshes clamped in one place. You can kind of go here and change the scale of the meshes to make them smaller, so that they're not so clamped. They're still pretty clamped though. Okay, so that is that, and this seems to be the best. Oops. This one seems to, according to the distribution, seems to be the best solution for this particular structure, and I can see why. It's basically quite even in the distribution, and it does have that cross bracing all over the place. So this is like the most optimal one. Seeing this kind of distribution, I would still revisit this and calibrate, especially the wellness score. I would calibrate it so that the distribution is a little bit more spread out. This means that sometimes the values are very, very high. Here, where is it? Why are the values very high? We don't see any meshes here. Oh, there are meshes here. So here, this guy is messing up the whole distribution. So I can kind of just click on it. I can click on it. There we go. And I can delete it from the view, right? Delete. And now the distribution is a little bit better, right? And I can then take a look at this one, which is also like, it has 4 wellness score. I can take a look at this one, and I can also delete it. So we end up with this. And basically at certain point, the distribution will start looking a little bit more reasonable, right? Okay, that is it with this one. Hope you enjoyed the tutorial. Sure was fun for me to do. Bunch of stuff. Sure was fun for me to do. And I will see you in the next video. Bye.